All right, all right. Welcome back, everyone. Today we have Guan Yu, and he'll be talking about cohomology theories. So,
Okay, so today I'm going to talk about the cohomology theory in algebraic geometry. But before that, let me start with some review of classical um, algebraic geometry. Um, okay. Maybe I need to change the color and is it this one might be much. Okay. Um, okay. So what we have for any suppose R is a commutative ring. Let's say over K, K is a field. You should think this as complex numbers if this is actually the first course, crash the course of cohomology theory in algebraic geometry, it's better to do it. So in my mind, I understand the cohomology theory using complex geometry, but doing every technical things using algebras. Now, we have a space, which is a scheme. Um, okay, spec of R, and it has a structure shift, let's denote it by O spec of R, O subspec of R. This is also denoted by R twiddle. So this means that for any this means for any R module, we have twiddle, which is constructed as an spec R sheaf. Okay. And wait, can I move it? Can I move the yes. No, no. How do I move it actually? All right. How can I move to the old one? Yes, okay. So I don't know if Dr. Wang talked about it last week, how to construct this, but this is the way how you get this is the way how you get a quasi-coherent sheaf. So how do we think about quasi-coherent sheaf? It's you could think of them locally as modules and then glue together because we are talking about a affine scheme, then everything local is global. So it's literally a module. Now you can actually construct a one by one correspondence between the cohomology of sheaves and the category of quasi-coherent sheaves and R modules. And it the category contains a subcategory which is coherent sheaf. And you should think when R is Noetherian, then coherent sheaves is equivalent to say this module is finitely generated. So locally, we have very good interpretations of what QCO and CO is. Now, move to the next step is that not all schemes are affine. There are a lot of other schemes. For instance, we could take En over k, which is approach of k adjoint of n plus one many elements. So this one is a little bit different. So how do we see this? How do we see this one is different from the affine space? Now we have affine space, let's say this is y, and we have x is spec of some ring, then all the global sections of X with its structure sheaf. What is this thing? This is, you could think as like all the rational functions on your scheme, and because it's itself local and everything should be locally, then all the rational functions on it are just the defining rational functions on it, which is R. And this is basically how do you why scheme is useful, that the space is determined by its functions. Now, okay, we have this, but for y, then we have the global functions of y, which is projective space, and we have this thing. There is nothing non-trivial global functions on it, which means that all the global functions is the field itself. So how do you think of this? This is in the classical geometry is called Liouville. Now you see that this thing behaves very different affine scheme. Now how do we detect other informations if we don't have global section, if we don't have enough many global sections? Here is this is question. How do we get um other information? I'm very weak here. By other information, it could be anything. So to really answer this question, it's okay. We have we don't only have global sections, and the local sections are also telling us a lot of information. If you know something in complex geometry, it's like the meromorphic functions is telling you some global geometric information. And that's our how do you say the principle here. Now, okay, to really talk about the technical things, we need some categories. Now we have, let's say X is a scheme, over K, and coherent O of X is the category of all coherent sheaves over X, which is contained in QCO over X. And this is category of quasi-coherent sorry, QCO coherent, and this is contained in OX. This category is called OX mod, which is the category of OX modules. And this category is contained in sheaves over X. All of these categories are abelian categories. So we can do, because we have a very powerful tool which is called the homological algebra, we can talk about the many things using homological algebra. And by classical homological algebra, we have a functor. This is a functor from the category of sheaves of X to the category of abelian groups, which takes all the rational functions defined on X. This is this functor is left exact. How do we see this thing? How do we see this thing? Well, restricted to the subcategory of OX modules. So why don't we care about all the sheaves, but we care about all the this subcategory of OX modules, because we already have a structure sheaf, and the structure sheaf is telling us a lot of geometric information. So because we have the structure sheaf OX, it contains the geometric information, meaning that how the functions are glued together and the geometry on the space is determined by the functions. So we don't care about all the sheaves, but the OX modules, which carries out the geometric information. And this functor is left exact to restrict onto the subcategory because is isomorphic to the functor of OX modules from OX mod to abelian groups, or this is actually k-vector spaces. Because we know that this functor is left exact automatically. The global functions is left exact, and we know that homological algebra tells us that we could take the left write the functor of a left exact functor. So the cohomology hi of x with coefficient f is OX module. This is defined to be the formal cohomology of derived functor of hom OX applied onto F. Now, another question is question 1, does this construction make sense? What do I mean by this? The answer is okay. Meaning how do we construct the cohomology? It is because this category OX module has sufficiently many injective objects. So for anything F, it could be having injective resolution and Hi of X with coefficient f could be computed as the formal cohomology of global function applied onto one of the injective resolution. And we know that from homological algebra, no matter what choice you have, you give the same cohomology group, and this is well defined. So it does make sense in the sense that there are sufficiently many injective objects in the category of OX models. Any questions before I move to the next? Okay. Now we need to talk about some properties of the cohomology of sheaves. So the first one is when X is affine R is an Noetherian. We know before that this global section contains all the information, which means sort of we don't need the higher information to know the geometries of this space. And we don't need means that all the things might be trivial, and it's actually yes. So cohomology of X with coefficient f, where f is X quasi-coherent. We need the Q code over X. Then yeah, let me just erase this. Then the cohomology in the cohomology is higher cohomology is 0 for I bigger than 0. So in this case, what it means is that we don't need the higher information to really talk about the geometry of an affine scheme. Well, we quote unquote don't need that. Okay, so why it's true? Some proof sketch or idea. This is the only proof I'm going to talk about today because I want to show something here, which is sort of I don't know, should be called the principle of algebraic geometry or the technical part of I don't know. So it's like geometric properties of a scheme um, is let me say approached by algebraic tools. You will see that there are a lot of quote unquote meaningless algebras commuted by algebras here, but in the end, it is really showing that this result. So what is the proof idea? And the first step is you have to show when I is injective R module, yes, then the natural map from I to I sub j, where this is localization with respect to an element F, this is surjective. The second step, using this, if I is injective, then the sheaf associated with this ideal or module is flask. What does this mean? It means that this is an injective sheaf. Now, if to I is an injective resolution in the category of R modules, then we take all the sheaves associated with it, then we know that this is a resolution in the category of OX modules. And we know how to compute the cohomology by doing it on okay, I need another. Then the cohomology of X with Twiddle is the same as HI of gamma X applied onto injective resolutions. Did I make something wrong? Yes. Yeah, I just noticed this. Sorry about that. This should be coaching. Everything should be coaching complexes. Everything should be coaching complexes. Did I do it correctly? Okay. Now another thing that since we have know how to compute it, we can just do the computation, and then we know because we know this sheaf comes from we know that this sheaf comes from a module, then H, the higher cohomology of this part. Did I do something? Okay. Just 1 second. It seems there's something wrong. Okay. I don't know why there is such a okay, it could be erased. All right. So by computation, is 0 for I is greater than for higher cohomology. Now, it's not really a proof, and you see that there are a lot of gaps which should be filled with algebraic commutative algebra. But what I want to say is, if you want to get some geometric property of schemes, you have to like use commutative algebra, and the geometric properties are carried out by the algebraic constructions. Okay. Now this is the cohomology of And furthermore, the converse is true, which means the following. Um, the following are true. That first one is X is affine scheme. The second is that higher cohomology of X is 0 for I bigger than 0 and all quasi-coherent shapes on X. And you see, it's not only the higher cohomology does tell you something that if this scheme is local or not by the second property. Any questions before I move on to the next part? Okay. So after talking about affine schemes, then the next one is some non-affine scheme. Let X be broad of S, where S is the polynomial algebra of n+1 variables. And then we say OX1 is the twisting shape of cell. How do I think of this? This is you have us with 1 degree shift and you take the sheaf of it. Then this is another way of thinking about it, algebraic. Then we have the following. First is us to the global section, but twisted version, which is defined in this way, taking in all the integers, the global section of X, but all the twisting shifts over X, then this map is an isomorphism. I will explain what it means slightly later. The second one is we know the cohomology of this kind of twisting shifts. This is 0 for wait, I'm making a mistake. Okay, let me say D is different from N because I also have N here. I is less than D, bigger than 0. Between the for all the twisting shifts between the dimension and 0, there's nothing inside, and outside there's nothing. The only possible non-trivial part is H0 and the dimension of it. And we know what are the things that are not equal to 0, which is H D of X. Then you need to twist it by minus D minus 1 times, then this is isomorphic to the field K. Now this is something telling you the cohomology of projective spaces. And you might think that this is, how to say, very technical, useless, but actually it's not. Basically, I would like to say all the classifications of curves and surfaces, maybe some other things, all the things are really rooted back to the computation of cohomology of the twisted shapes on projected spaces. This is like the very fundamental theorem of all the classification theorems in algebraic geometry. And let me talk about it a little bit. Um, so let x over k be a proper scheme. Proper. How do we think about a proper scheme? It's although we really didn't do the techniques, but you should think of this as compact. This is really the compact analog, compact and Hausdorff. Condition in the category of topological spaces. So when we're talking about proper scheme or relative proper scheme, we're talking about compact and the Hausdorff varieties or topological spaces or manifolds in the Eurosense. If we have such a thing, L over X is invertible sheaf, then the following are equivalent. The first one is L is ample. Second, for any coherent sheaf over X, they exist a number n0 depending on f, such that for any n bigger than n0, the higher cohomology of X twisted by L n many times, this cohomology is 0. The third one is okay. L is very ample. L test many times is very ample, but that's another definition of being ample. Anyways, so what does this mean? I don't know. I don't know. So the conclusion is corollary. This gives an embedding or at least the immersion. Let's say to be safe, immersion of X into some projected space. And this projected space is given by this ample line model. And what does this mean? After immerse it, or after immersing it, after embedding it into some projected space, we really know the geometry of our space. And that's how we study the geometry of algebraic schemes. I will talk about some very famous theorem about this maybe 10 minutes later. This And another thing is, okay, I need another one. This is essentially, this is basically how you, uh, which is in reality how you compute the cohomology of schemax. Any questions about what I have talked about? Okay. Uh, if not, I'm going to talk about more fancy theorems. The first one is um, duality theorem in algebraic geometry, which is the shear duality. I'm going to only write down the duality for P and the projective spaces, but this could be generalized to any projective scheme. Now let's X be n over k and omega x. This is the dualizing shift is defined to be the wedge power, the top wedge power of all the differential forms of x over k. Now, then here this is the following. The top cohomology of this dualizing shift is one dimensional. And you need to fix such isomorphism then for any coherent shape of x, you have com from F to your dualizing shift tensor with the cohomology, the top cohomology of the coherent sheaf, then we see that there are two things. This F and this F is going to be cancelled, and canceling this is having the cohomology of X with respect to the dualizing shift omega sub X, and we know that after taking one isomorphism from the first part, it's the field itself. Now, this one is a perfect pairing. If you really recall the classical Poincare duality, then you see for Poincare duality there is equivalent statement saying that there is a perfect pairing. And this is the analog inside algebraic geometry of the Poincare duality. And you don't here, well, here you need the smoothness, but actually, in the full generality, you don't need the smoothness. And the third part is saying, I have extension group of F to omega, and this is isomorphic to HA minus I of X with respect to F, but you need a dual because you want this one a functorial isomorphism. So you see that in algebraic geometry we have a duality theorem as well, and this goes back again the understanding that proper should be thought as equivalent to compact in the Euro 6. This is not true for non-proper. The duality theorem is not true for non-proper schemes or varieties. Similarly, the duality is not true for non-compact manifold in classical topology. Any questions? Okay, so the next one is the famous Coda-Euro vanishing, which says if X is proper, smooth over complex numbers, and L is an ample invertible sheaf. Remember that ample sheaf gives you embedding inside the project space. Then the cohomology of L tensor with your dualizing sheaf is equal to 0 for I bigger than 0. Now, using shear duality, you have a common thing saying that the higher cohomology of the dual sheaf of your ample invertible sheaf is equal to 0 for I less than n. It seems it's something nonsense, useless at the beginning of the Coda-Euro vanishing, but it's really useful in the sense that there is a principle saying that a vanishing, let me say, a vanishing theorem implies embedding theorem. What does this mean? This means, well, in this case, the Coda-Euro vanishing theorem is the key tool for the famous Coda-Euro embedding. Which says basically gives you ample line bundle, whether it's positive or not, the equivalence condition, whether it's positive or not, really gives you for a compact, complex manifold, when could it be embedded into project spaces? So you could say, okay, I want to add something more here, which is a good vanishing theorem implies a good embedding theorem. Well, Coda-Euro vanishing is a good vanishing theorem in the sense that it tells you a lot of embedding information. So here there is a problem that before we are talking about, for instance, this is cohomology theorem, algebraic geometry, but the right-hand side is cohomology in complex geometry. And the cohomology in complex geometry is nothing but the cohomology theory in topological spaces. Are these two very different things giving you the same answer? And yes, oh no, oh no, I'm running out of all the whiteboards. Okay, let me finish everything probably within the last one. Um, okay, um, this is what Gaga tells us that for X to be a projective variety over complex numbers, we have the algebraic way of computing the cohomology um, with half a quasi-co let's say coherent sheaf, uh, coherent, then it is the same as the Euro cohomology of the analytification space of X with the analytification of the sheaf. So this is telling you that we have very different constructions of cohomology using algebraic way or the topological way. But in the case of projective varieties, whether you have smooth or not, then they are exactly the same. This is a functorial isomorphism. So this is a very important and useful thing, which remind us for this part, for the topological cohomology, they are very good things, which there is a very good thing which is called the Brown representability. Brown representability says that if H and something is a reduced mineralized cohomology theory, then Hn of I, Hn, this function could be expressed as the pointed mapping space to some omega spectrum. And in the case where this generalized cohomology is taken, the Euro cohomology, our spectrum could be taken as the Allenberg-MacLane spaces. This is saying sort of on the right-hand side, we have a universal cohomology. Then the same question is asked here. Do we have a Brown representability theorem in the field of algebraic geometry? And the reason why I want to talk about it is because it seems not. We talk about cohomology theory, but there are other cohomology theories in algebraic geometry as well. For instance, I do not suggest we talk about it, but they are Idal cohomology, and they are Bristolian cohomology as well, and they are algebraic de Rham cohomology. And when all the things are defined, they turn out to be the same in some cases that we care about. So this really means that we probably it seems not easy to have a universal cohomology theory in algebraic geometry. And the reason motives are introduced is because this phenomenon. So Gorthenick suggested that probably don't have a universal cohomology theory, but there should be something called the motives, and every cohomology comes from a motive, something like that. Then there is probably a universal motive, and this could answer the question whether we have a universal cohomology theorem. So, Professor Hoffman, you want to say something?
Yeah, let me jump in here a little bit. So you've described the Gaga theorem,
Yes.
right? It's true. What you say for a coherent sheaf and a projective variety, you have a comparison between. So on the left-hand side, you have the Zariski topology on X,
Yes.
and on the right-hand side, you have the analytic topology,
Yes. Yes.
right? And of course, this is a very non-trivial fact. It's proved by Serre. Now, first of all, I have to point out, if X is not projective, but is only affine, it's totally wrong.
Right. Right.
So it's very, very important to understand that the completeness of X is absolutely essential for that statement. If you take an affine variety, those two things are very, very different. And one way of thinking about that is the following fact. If you have a meromorphic function on the Riemann sphere, now that's the projective line, it's a rational function. It's a quotient of polynomials.
Yeah.
But if you have a meromorphic function on just the affine line, you can have e to the z.
Yes.
It's a holomorphic everywhere. Of course, it has a very essential singularity in infinity. So Gaga is totally false for affine varieties. Okay? So that it's very crucial to understand that the Gaga theorem is a theorem about complete or projective varieties. Now, the other thing I want to point out is when you jumped over to the Brown representability theorem, you're changing the narrative in the following way. Brown representability doesn't deal with coherent sheaves. It deals with what we would call, well, constant sheaves or locally constant sheaves, or more generally what are called constructible sheaves. So when you have, so there's the coherent world, there's the world of coherent sheaves, and then there's the world of constructible sheaves. Very, very different objects. So when you're talking about Brown representability, you're not talking about coherent. There's no hope to represent the cohomology of coherent sheaves by a Brown representability theorem.
No.
Right. So what you're saying about these Eilenberg-MacLane spaces really refers to constant coefficients, for example.
Yes. Right.
Right. So, and indeed, now what you started to say over here about Étal and crystalline and Durham. Now you can talk about coherent sheaves in those worlds. It's perfectly okay. But generally speaking, what Grothendieck was addressing were the constructible coefficients, not the coherent ones. So in other words, you want a Tal cohomology with coefficients in ZL, the L-adic numbers, or QL. Yeah, say ZL, QL. But QL is not a coherent sheaf. Oh my God, no. It's that thing is really understood as a constructible sheaf. You see, it's more like a constant, the sheaf of constant coefficients. So you have to keep these different worlds separated when you discuss this. Okay, that's just my comment.
Yeah, thank you so much. Yeah, maybe I was in a rush at the very end, so it's like, yeah, thank you, Professor Hoffman, to point it out that yeah, here I really should say also I don't have um the cohomology, singular cohomology of z coefficients is the same as the singular, sorry, the check cohomology of constant, constant, constant sheaf here. And this is in the algebraic topology side, and in the algebraic geometry side, you have the cohomology of something is the same as the check cohomology if your space is no theory. So there are some similarities here. So one would like to have a bridge from algebraic topology to algebraic geometry or the other way around. So sorry for that. I missed something that was in my head, but that's basically all I wanted to talk about.
Well, let me make one other comment. There is an application of the Brown representability theorem to prove the duality theorem. Now this is a very very ingenious argument due to a guy named Amnon Niemann. And what he did is he uses the derived category. Now in the derived category, under certain circumstances, he can prove a Brown representability type theorem. And using that theorem, he can give a proof of Grothendieck's duality theorem. It's a very ingenious argument, but it goes into the derived category. Okay, but I just point that out.
Thank you. Thank you for the comment. I suggested last week that Houghton could talk about the derived categories of coherent sheaves or bounded derived category of coherent sheaves. They are a huge industry on this topic, and Niemann is kind of he's an expert in this thing. I read a lot of things from him, like the Grothendieck duality things or some other things. Those are something that I like pretty much. Derived categories could be viewed, I don't know, but I think derived categories could be viewed as the categorification of the cohomology theories in some way. I don't know how to like make it precise right now, but this is cohomology is really computable, and that's why it's really helpful for us to say like the classification of curves, surfaces, or those kind of things. So yes.
Yeah, one other comment. When you say computable, there's software that does this. You can do this in Macaulay too.
I'm running a package right now. So for
yeah, or Singular. I mean, there are packages now that will actually compute rather efficiently the sheaf cohomology of various kinds of spaces. So this has really entered the world of technology.
So actually, I can show here how to do it. I do have the Macaulay too. So Crescendo didn't really introduce me, but I come from Cornell, and I'm now writing Cornell as well. One of the author of Macaulay too is Mike Stillman, and he's in my committee actually. So we can try it out here. Cohomology is really done by extension groups. So we can wait. Well, maybe I'll do it next time. It's over 1 hour, so maybe I'll just do it next time. Next time I could show everyone how to use Macaulay to compute some cohomologies or even cohomologies of complexes of sheaves.